All right, so I want to give you an overview of Docker and containerization. But before we go into how to set it up, all for you to learn about all the different commands of Docker, let's stay high level. So let's switch over to my iPad where I can use this to explain about the history of containerization, Docker, and why this is really important. Docker is something that has really revolutionized how web applications are done. It's a game changer. So for any software engineer who's interested in going into web development, you have to know Docker and containerization. If you don't, you're not understanding something that has really become a critical piece of software development. Okay, so having said that, let's talk about containerization. Okay, so what is containerization? Now, in order to address what containerization is and why Docker is really important, I think it is important to go back a little bit earlier. Okay, so let's go back to, let's say, back in the 1980s. So if you were to go back in 1980s, how did people create web applications? Or let's say in the early 90s, maybe web was, still too early in the 80s. So this is how people deployed back in the day, right? So let's say this is back in the day. So this could have been in the 80s, maybe even, early 90s. Okay. If you were building a web application, what you could have done back in the day is you go and get a computer. So let's say this is my computer box, and the computer comes with certain memory. So let's say, I'm just going to use today's kind of, RAM, but let's say it came with, let's say 8 gigabytes of RAM, which really wasn't really available back then, but we'll just come up with that. And then it came up with some hard drive. Okay, so you would go and go to a store, buy this physical computer, and you would install your program here. So you can install, for example, PHP, or assuming Node.js was available, you could have installed Node.js. Node.js wasn't available back then. But anyway, you can install this, you can install different programs in this physical computer, and then you basically connect it to the internet somehow. And when people send a request to your to your domain, it's this computer that would be running things behind the scene, running these programs, and it would deliver the HTTP response. Okay, so this buying a physical computer like that, buying a physical computer server, is what people used to do back in the day. So if your startup was going really well, what do? You buy more computers like this. And these computers were very expensive because, it needed to be high end. And then if you get multiple computers, how do you get them to actually work in harmony so that it's coordinated well? Well, you also have to set up a network and, blah, blah, blah. So this is how people used to do it back in the day, by getting a physical computer. And so, starting a software company, and once it goes big, a lot of money was spent on buying actual computers. Now, a lot of this has changed when there was this thing called virtual machines. So go to Wikipedia, spend maybe 5 minutes learning about what virtual machines are. But virtual machine really, combined with cloud, has really changed this industry. So unlike previously, where people will go buy and set up different computers, maybe they have a room where they put a bunch of computers, put cooling fans and AC so that the computer doesn't get hot. Now, with the virtual machines, this has really changed the game. So, to kind of give a very high level overview of virtual machine, just imagine that computers got better and better, and faster, bigger, with more RAM, more hard drive. So now it was possible to get this really, really powerful computer. And what they were able to do using a software was within this, computer space, basically they would create multiple virtual machine and say, okay, let's say 8 gigabytes of RAM is available for this giant computer. I'm going to dedicate 2 gigabytes here, 2 gigabytes here, and let's say I have 1 terabytes of hard drive. Maybe I'll dedicate 200 gigabytes of hard drive here, 200 gigabytes of hard drive here, and they can set up multiple virtual machines using software inside a single computer, okay, using software. So what this allowed to do was, as the computer got a lot more powerful, companies with a lot of money could buy a lot of these very nice computers that would cost a lot of money, and they could use software, virtual machine, basically to break it down into smaller chunks. And within each virtual machine, it's as if you're actually having a dedicated computer with that much resource in RAM, hard drive, CPU usage, and they can access this. And they can install their own software in here. They can install their own software here, different programs here. So it's as if there's actually a separate machine. And users actually don't know the difference. So again, this was kind of the Web 1.0 version where people actually bought a physical computer. But with a virtual machine, now companies like Microsoft, Amazon could buy a bunch of these nice computers, set up a virtual machine, and rent these virtual machines. So imagine, Amazon could go buy these, giant computers and say, okay, I'm going to set up a virtual machine. This is going to have 1 gigabytes of RAM, 100, gigabytes of disk space. And, I'm going to dedicate this amount of CPU power to this virtual machine, and I'll charge you, maybe 30 cents per hour to rent this virtual machine. And, maybe I'll have 2 gigabytes of RAM here, and I'll dedicate more CPU power, and maybe this one I'll charge you 45 cents per hour, and so forth. So notice how this virtual machine has really changed the game. Back in the day, if you're an entrepreneur, your company's going massive, you raised a lot of money, and with that money raised, you bought a lot of these expensive computers, you connected them, set up load balancers and other things. But now, with virtual machines, it allowed these cloud companies to form, or cloud services, okay? So this is where, for example, Amazon bought a bunch of computers and they put it in a warehouse, some in Virginia, some on West Coast, some in Australia, in different places. And they basically, within each of these computers, they set up all these virtual machines, and they basically allow people to rent and pay an hourly. And if they didn't use it, then they could not pay for it. They only pay for the usage. So if you don't need 100 computers, maybe you only need 20 computers now, and maybe when your application gets a lot of traffic, maybe you want to have a lot more. Well, this virtual machine basically allowed these companies to set up these services in a way and allow people to rent. So it's almost like the Web 1.0 where people bought the actual computer was like buying a home. Now you can actually rent these computers at an hourly cost. That changed a lot of things. If you look at Microsoft, Azure, Amazon, the EC2 servers, the cloud services, Google's getting into it. A lot of big IT companies have gone into this cloud movement, which is basically, hey, don't go and buy your own computers. We actually bought and will maintain everything. Why don't you just rent some resources from us? And what allowed that to happen was a virtual machine. And you could say that virtual machine was a game changer, right? It really changed how people built applications and deployed. Okay, so now we talked about virtual machine, okay? So virtual machine is not an actual computer. It's within a computer, there are multiple virtual machines. In fact, even in your own laptop or desktop, you can set up multiple virtual machines with different operating system and things. Okay, now let's look at virtual machines. Okay, so virtual machine runs very similar to an actual computer. It has dedicated amounts of RAM, dedicated amounts of hard drive, and then dedicated amounts of CPU that you can dedicate. So in your own computer, you can set up 3 virtual machines, all with different operating system. Okay, so let's talk about how we would deploy an application to a virtual machine. Well, you log into a virtual machine using terminal. And then this is where you basically install different operating system and software. So you would go access this virtual machine remotely using the terminal, and you would install maybe Windows or Linux, or you would install these different software one by one. If you're using PHP, you would install PHP. If you're using Ruby, you would install Ruby. You would install these frameworks, libraries, dependencies, and then you run your applications in this. Okay, so that's just like, if I give you a new computer and say, hey, get your web server working on this computer, you can imagine you would go and install the operating system, install all the program one by one, and you would, see if your app is working right. Okay, so again, this is kind of the Web 2.0 version of how people used to deploy applications by accessing these virtual machines, using terminal, setting up these programs, and so forth. Now ask yourself a question. If I give you a new physical computer and say, I want your application to work on this computer, how long would it take for you to set up that new computer so that the new computer is running the application, your application, flawlessly? Could you do it in seconds? Can you do it in minutes? Can you do it in hours? Probably will take you a few hours because you have to install programs, and maybe the operating system you're using is not the same one as the original one you're using. Maybe there is some conflict. Maybe some of the software you're installing doesn't work for that operating system, or maybe the software you installed on your original computer was version 3.1 and the new one you downloaded was 3.5, and maybe the 3.5 doesn't work well with 3.1 and so forth. So anyway, you can kind of anticipate that, yeah, it's not so easy to get an application that's working on your local computer to work on another machine, right? So back in the day with Web 2.0, this is why there were people who were dedicated on managing these virtual machines. So software engineers would build a code base and say, okay, it should be working, but it never really works exactly the same. So they got these people called DevOps who were responsible for setting up these virtual machines, making sure it's running the most updated operating system, the version, the dependencies, different software, and they would maintain it. And let's say, oh, you're using PHP 5 and now there's PHP 8. They would go and they would update virtual machines and make sure it's working flawlessly, that there is no bug, no major security flaws, and they would set up monitoring tools to make sure that the virtual machines are working well and so forth. Okay, so that was the role of the DevOps. Now, this is interesting because all the virtual machines have really kind of made the software development and deployment a lot better. It still had some flaws. Some of the flaws we talked about, how there are all these dependencies and your software may work maybe well on your Mac, but it may not work well on a PC and so forth. Okay. All right. And, back in this day, it was very common. Let's say, there's a developer 1 and there's a developer 2. And on developer 1 on their computer is working fine. And then, developer 1 says to developer 2, hey, get this code, on your running on your local computer, and it just doesn't work exactly the same, and they troubleshoot, right? They're like, okay, is it the operating system? Is it that you're running a different version than what I'm doing? And, they go back and forth, try to figure out what's going on, right? So if you worked with other developers, you probably had these cases where your code is working fine on your computer, but when you get it to deploy on someone else's computer, it just doesn't work. Again, it's because, maybe on this computer it's using certain operating system. Maybe it has some other programs here that look different than the programs that you have, and therefore you have to sort it out. Okay, so that was kind of, how things were done. Okay, now introducing Docker and containerization. So containerization, we can go and you can read quite a bit about it. We can go pretty advanced. But in a nutshell, containerization is kind of the next step, next evolution of virtual machine. So notice that with virtual machine, let's say this is my virtual machine, I still have to install my own operating system. I still have to install my own programs. And this would usually takes at least a few hours to set it up, right? And if you have done deployment using this, then you also have to make sure, do I have the right ports open? Did I block certain ports that I don't want people to access? Do I have the latest software for the things that I need? And this is a full-time work. Now, containerization is really unique in that so it's similar to virtual machine in a way that it revolutionized the way that things are deployed. But what containerization does is it basically contains everything that your web app needs. And in a way, you don't actually have to install a whole new operating system. So the operating system layer has been removed. It's not in the container, but it has everything you need. All the software that you need to run your application would all be contained here. And we'll talk about exactly what it, how to do it and what this means. But the beauty of this is by putting everything that you need in a container, if it works on your computer, you can basically put this container in someone else's computer and it will work exactly the same. So now you don't have to worry about that going back and forth and be like, why it's working on my end, why is it not working on your end? Okay, it solves that very, very beautifully. In some ways, notice how this changes the game of DevOps. In the past, DevOps needed to be the one to make sure all the programs were installed the right way, they were maintaining it, but now developers could actually just containerize everything that's needed, and now all they need to do is just deploy this into the virtual machine, or now Microsoft, Google, they all offer different services to manage these containers. So it really reduced the amount of DevOps work, what they used to traditionally do. Now it's up to the software engineer to build and manage these containerizations. So it made the job of a software engineer a little bit harder or a lot harder, especially when you're learning Docker and containerization for the first time. But it did really change the game. What's also really, really amazing about this is very lightweight, and you can deploy this in seconds. How long does it take once you set up a virtual machine for you to launch a new virtual machine? Minutes, maybe not hours, but it would take minutes. Now, are customers willing to wait minutes? No, usually after 5 seconds they leave, right? But what containerization allowed, because new container can be launched within seconds, is super efficient. It just changes the whole game and reduces the amount of work of maintenance. And there are all these other benefits that comes with it, okay, which I'll explain a bit. But anyway, that's kind of the history of how web applications were built and managed before people actually bought a computer and did it. And then with the virtual machines, now you could have multiple virtual machines within a physical computer. And now it's almost like within a virtual machine, you can deploy multiple containers. and you can do it in seconds, right? So it kind of went through these evolution. So containerizations is relatively new as the time of this video, which is created in 2021. But it did really change, and for the last 5 years or so, it has really caught a lot of momentum. So a lot of developers in Silicon Valley and in a lot of top companies are always building things using containers. They're no longer going directly to the virtual machine and deploying. They're working in containers. So it requires additional steps for you to do, but it just fundamentally changes the game. It really does. So this is why learning virtual machine is really, really important. Okay, so let's talk a little bit more about some of the concepts. So there are some terms that you're gonna hear about. So I want to just kind of get you ready on some of those terms. Okay, before I talk about some of these terms, maybe it is good to show you some examples of how Docker works and some of the files that you may end up seeing. Okay, so let me switch my view to this. This is the Hacker Hero code base. So it's a private repository on GitHub. We have some documentations on this, and the README. This is the web backend. This is the folder that contains the code base. But notice here that we got controllers, models, views, routes. We are using Express. We've customized Express to make it more modular into an MVC framework. But notice that there is a Docker file here, and there is a Docker compose, and there is a package.json. So depending on the program language that you've chosen, there are ways to manage different dependencies. But for Express, for example, there is package.json where you can customize and say, hey, for this application, I'm going to name it this. This is going to be the version. This is the main file. These are different commands that I want to run using npm. These are the different dependencies that my code depends on with specific version number and stuff like that. So package.json file is really important in managing dependencies so that we outline exactly what version of different modules that we need and so forth. Okay, but you will see that there are two files here that are interesting. Okay, one's called Docker file, and one's called the Docker compose file. Okay, why don't we look into a Docker compose file? So, there will be videos and other tutorials that we will refer you where you can spend more time to read and understand about Docker compose file. But at a high level, the important thing I want to point out is the services component. So notice here, we have services, and then we have multiple services that we said, hey, this one called it DB, this service called it Redis, called this Selenium Chrome, called this app. And on some, we have this thing called the volume and the image. Okay, and the image, and the image, and then also the image here as well. Okay, so what does that mean? All right, so let's go back to the iPad. And let me kind of explain that a little bit so that you understand at a high level what's happening. All right, so the way that you work in Docker is by, okay, so first of all, the concept of an image. So imagine at Docker repository, there are a lot of different images that you can pull. So if you want, for example, so I'll call this a Docker repository. If you want a specific MySQL, let's say version 5.1, they have an image here that you can use. It's in a public repository. Think of it kind of as a GitHub repository tool, but where there's an image that you can use with existing software. So this one could have MySQL, this could have a Redis database, maybe this one has a Node.js already installed, maybe this one is an Alpine server, and so forth. So there are all these images available that you can use. And if the software are open source, you can probably find them on Docker repository and you can use it. Okay. Now you can use these images to build a container. Okay. And when you're building your application, you could, for example, have multiple containers that are doing different things. Okay, so I'll try to bring all of that concept together. Okay, now notice that there was also this term called services. Okay, so let's talk about image. And using an image, I can create a container. And using containers, I can create what's called a service. Okay, so can just kind of, think of that hierarchy. Using an image, I can create a container, and containers are the actual working apps. And then I can, using container, I can build services. So if I have an application, so this is my Docker containers. I could have, for example, a service called DB or MySQL or whatever, and I can tell Docker, hey, pull this particular image and set it up on this port number and so forth. Okay. Oh, I also want to create a service called Redis or whatever you want to name it, and I want Docker you to pull this image and get it to be working and so forth. Okay, does that make sense? So let's think of, for example, like the wall assignment. Okay, if you think about the wall assignment, right, you have, let's say you're using MySQL, version blah, 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 right? You can tell it, okay, grab that image, and I want to call it MySQL, and I want to have this have a port number. So, let's talk about the port number a little bit later, but you can set it up, and let's call this a MySQL service here. And then imagine that, for the wall assignment, you're also using Redis, to maybe, manage your session. So you can create a service here called Redis, and you can tell, okay, grab, this image from the Docker repository and, open up this port and blah, 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 and you set it up. You would also need your custom application. So you can name that service again, app or whatever you want. And for this custom app, there is no image in the Docker repository. Maybe you can put it there, but if you don't put it there, you can say, well, this one don't pull it from Docker, but let me actually tell you where the image is. Okay, so this is what you can do. So once you get this up, and this is the role of the Docker Compose. Docker Compose YAML file is for you to outline all the different services or containers that your application needs to work. Okay, so that's the role of the Docker Compose file. And you will learn more about, each of the syntax, what to type, how to set a volume, how to have it connect with each other. So this app is talking to this app is talking to that app, and so forth. But that's what a Docker Compose file is. Okay, now remember when I talked about this custom app, there is no image, right, out there in public. You need to build it, right? So that's what the Docker build file is, or the Docker file is. You create your own Docker file and basically tell Docker how to create this image. So now let me switch over to this computer screen. So notice that what I'm doing right now is there's also a Docker file. So this Docker file is basically outlining, okay, this is my custom application. So I'm going to tell you how to build this image for this container. So you can say, okay, build it from node, blah, 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 right? And then from this directory, run this command. Okay, I want to define this as my working directory. Copy the package.json, run npm install, and then, copy this and then expose port 4100 because, in this app 4100 was open. So it opened up port 4100. So this Docker file is used to create a single to create an image, right? And then the Docker compose file is used to lay out the different services that I need for my apps to work. So notice that I have DB, Redis, Selenium, Chrome, and for each of the service I outline which image to pull from the Docker repository. But for this app service that I've created, which I told it that it depends on these other services, DB, Redis, and Selenium, Chrome, I say go ahead and actually build it from the current Docker file. Okay, and then name this image this. So notice I'm creating my own custom image because hey, this image is unique. It's not available on Docker repository, and you may not want to make it available on Docker repository because you don't want other people just to grab your image and deploy your application for free, right? You want to hide it. So anyway, that's why for our custom app, we almost always build it ourselves, and then and then so forth. So another thing I want to go over is a port number. So when you get into the Docker file, you may initially get a little bit confused on, okay, what is this thing going on with the port number? Now, this is what you need to have in mind. Notice that Docker containers is its own environment, right? So if I have one service here, another service here, another service here, you have to open up different port for this software. So in this case, you may say, do you know what? I'm going to have this work on port 4100. And I'm going to have this one open on port 39 and this one port 57. So internally, within these Docker containerization, these services can talk to each other using these internal ports. So that's what I'm going to call as internal ports. Now, there is a way that you can say inside these containerization, I want this to be port 4100, but I also want to create another port called 4150. And when people from outside the container is talking to me, have it listen to port 4150 and have that reroute to port 4100 and so forth. Okay, so switching my computer screen again, if you look into some of these port number, that's what it means. For example, ports 3307, 3306, it means that within the containers, right? So inside these containers, it's going to speak in port 3306, but outside the containers, to the Docker host or to the outside, will actually have it be port 3307. Okay, and same thing on this one. Seems like on Chrome, we said port 4444, both inside the container as well as outside. For my app, yeah, so anyway, so that's what port numbers mean. We need to specify a port number inside the container and also define the port number for outside. Sometimes we may have services where we only wanted to talk internally. We actually do not want to set up another port number to have them talk directly to that service, right? So anyway, that's why port numbers are important. Okay, so let me take a breath a little bit. There are a lot of concepts that were covered over here, but at a high level, we did cover kind of the history, the Docker compose file, the Docker file, the port number, and the role of package.json and so forth. Now, this is interesting because the way that the Docker containers work reminds you of this new movement that web development is also going, which is called the microservice architecture. So I want to talk about that a little bit. A microservice architecture, an opposite of that would be what's called a monolithic application. So imagine, let's say you're building Google PowerPoint slide or Google Doc, right? Something massive. If you're building that application, can you imagine building that in just in one language? Or let's say TurboTax Online, that's a good example. Would you build all of that in Python or PHP or Ruby in a single application? The trend is instead of creating one giant application in one language and one framework, it's better to break it apart to different services. So maybe, for example, for TurboTax Online, maybe you have a specific service, a specific app, where all it does is go and talks to the county records website and grabs the latest county data. And that's all it does. And then maybe you have another application that just does the website when people visit TurboTax Online. Maybe you have another one that all it does is it just computes, for example, the tax refund. So given certain input, it just does this output. And maybe that's written in Java. So anyway, the trend is for software application, you don't want to create one giant monolithic application, because if you were to graph the productivity, and where y-axis is the number of engineers, and if you were to graph the productivity per engineer, the graph kind of goes linearly in the beginning, but then it kind of tapers off and it actually starts going down, right? And the sweet spot for this, depending on the effectiveness of the manager, could be anywhere from 5 to 10 engineers working on it. Okay, so a small team works very efficiently. So that's why if you see some of the great tech companies, they modularized it, and each team usually has 5 to 10 engineers working on specific microservice or specific component. And then you have these different services talk to each other using APIs, exchanging information through various means, sometimes using XML or JSON as the intermediate language to speak between. And that's how applications are built. So again, if we were to look at TurboTax, maybe the way that it works is there are multiple services. And maybe this again is written in Java. This one is C#, this one is PHP, this one is in Node, this one is in just C++, and then each of these would have 5 to 10 engineers dedicated on just making sure that works. So anyway, notice how this is similar to kind of how Docker allows you to set things up. So using Docker and containerization, you can also easily set up these microservice architecture and have the applications work. Now, one of the beautiful thing about Docker and this is because we're creating containers, and we talked about how it's very easy to deploy these containers in seconds. Now there are all these other services that you can use that if you have, for example, 3 containers, right, within, or 6 containers for this particular service, maybe when you have a lot of traffic, maybe 6 is not enough, and maybe you need 20, maybe you need 50. So there are services that you can use to manage the number of containers for that service. So for example, a popular one is called Kubernetes. This was initially built by Google, but there are all these other service layers on top that lets you manage the number of containers within any service, and they manage that up and down. There's also Swarm, and if you go to Amazon and Microsoft, they all have their own different services to manage these containers. But at a high level, you can see how putting things in a container made it so much easier. Instead of even a virtual machine where you had to log in, install dependencies one by one, test it. Now, if it works in a container, it works across all the computers, other developers in the new servers. So it made it very, very easy to scale up and down and manage. Except it did create just more work for software engineers. Now software engineers have to know all of these on top of all the other stuff that they used to know. So the expectations for software engineering has gone up. But if you learn this, and if you get good at using Docker and containerization, it does give you a very good advantage. Okay, now one more thing. Talking about continuous integration and continuous deployment. So one of the things that you will learn later in this course is a concept called TDD. Docker combined with TDD allows us to do this new thing called continuous. Okay, maybe I'll do a better job writing. Continuous integration. So what does this mean? Continuous integration basically means once you make changes in your code base, let's say you push it to the GitHub repository, which is very common. If it is done in a containerized way, notice that you can deploy it very quickly into, let's say, a staging server. It would launch that new container into the staging. If you have test cases, it would basically run the test case, see if it passes all the test cases, and if it does, you can automatically have it give you some feedback, right? If it doesn't, you can automatically have it, for example, send you a rejection, and you can tie this in with GitHub also, so that if someone sending a pull request or they merge the code, and if it fails the test cases, then you can basically say, hey, your code fails some of these test cases, fix your code and resubmit, and then we'll let you know if it passed the test cases. So that's basically what continuous integration is. Instead of traditionally where everyone works really hard for, let's say, 3 weeks, and then you update the staging server and you see if everything is working, you test everything, and then, oh, it's working now, updating the production server. This continuous integration cuts that feedback loop significantly. So as soon as an engineer makes a commit or sends a pull request, you can automatically have some feedback and say, hey, you broke these 3 test cases. Go ahead and fix your code and resubmit. So notice how that cuts down the QA time. That also allows developers to get much frequent feedback and add feature by feature instead of having one giant update where this code and this code may conflict with each other. So this has really also changed change how software is managed and deployed. But imagine if continuous integrations are done really well and there are a lot of test cases and it's very reliable, you can take it a step further and say, hey, if it meets all the test cases, automatically deploy and update the production. Now that's kind of the highest ideal where it just goes and updates the production automatically if it missed the test cases. But it could be done in theory, and that's called continuous deployment. Continuous deployment is where you submit the new code base, and if it automatically meets the test cases, it automatically updates the production server. It's a little dangerous in my opinion, but theoretically it could be done. And if the project is very simple, it definitely could be done where you're doing continuous deployment versus continuous integration. Okay, so that's kind of at a high level how the history, there were a lot of information that were covered here. What I will say is there are a lot of tools available to learn about Docker. Sometimes it could be a little bit overwhelming. So we'll try to provide you some resources where you can level up very quickly. In the past, all these Docker commands where you create an image, where you create containers, where you manage the images, where you prune the images, where you go and access different containers and run different commands, it was very complex. You had to do everything in the terminal. But VS Code has really changed that, how things could be done. It's really, really powerful. And instead of you memorizing a bunch of terminal commands, you can do that in a visual way using VS Code. It's really neat. And also VS Code has some powerful debugging features where you can debug and listen to ports, and it's really beautiful. So in this course, we're going to have you focus on using VS Code so that instead of memorizing Docker commands, you can stay high level, still do everything you need using VS Code Docker extension, but you can get to experience TDD using a debugger and so forth. Okay, so hopefully that was helpful in giving you a good level overview. And now how to do some of these things and implement will help you through the rest of this course.